I have referred in the lecture on correlation, the previous module, number 12, to a powerful non-parametric method for removing the annual cycle. For example, the runoff anomalies just shown were obtained by that method from the original time series. Let me here show you how to do this. First, I draw the axis, horizontal for time t, vertical for the climate variable x. Yes, I know that some pseudo-mathematicians would find this way ugly. Real mathematicians and we do not care as long as a proper meaning is given to an axis. Then I have to be careful and label the time ticks. J for January, then F for February, and so on, till D for December. And this is the first full year of the observed series, the year 1900. And the series starts in November 1899, so we have another N and another D for that year. And then the next year is 1901, and so on. Now let us draw a theoretical curve, a sinusoid with period 1 year. The lowest value for January, the highest value for July, and then the lowest one again for the next January, and so on over the full time interval. So that sinusoid could be a model for, let us say, temperature. Next, we put in the observed values, the thick brown dots, monthly values for January, February, and so on. And also for the start of the series, November and December 1899. And here for this exercise, I put in observed values that have a minimum at around January as the sinusoid, but the maximum is already in April or so, not in July. That means the annual cycle in the observed series, it deviates from the sinus model. A fast rise with the beginning of the year, maximum already in April, and then a long-term decrease until the next January. Hence, the Fourier model decomposition in sinusoidal terms, it would not work well for this observed data set. Therefore, we do it better. We calculate the monthly averages. The November average, x bar n, we get by adding all the November values and dividing by their number, the number of years, 91. And this is the December average, x bar d. The month-wise averages, January, February till December, the plot of those values does capture the deviation from the parametric sinus shape. A fast rise, maximum in April or so, and then a long-term decrease until the end of the year. And it is this non-parametrically determined curve we do now overtake to remove the annual cycle from the x of I values in order to determine the anomalies cap delta x of I. That means from each November value x, we subtract the November average x bar n. And from each December value, we subtract the December average, x bar d. Here I write down the anomaly values cap delta x for the point number 1, November 1899, and point number 2, December 1899, and then point number 13, which is November 1900, and so on. This goes till point number 1092, which is October 1990. So, the example here on this page was for the case when we have monthly values. Then we subtract the monthly averages. In the case of daily values, we would subtract the daily averages. That means from each 1st of January value, we would subtract the 1st of January average, and so on. In fact, this was what I did for the Elbe runoff data in our example in the tutorial. However, that would be difficult for me to draw here on this page. Hence, I showed this non-parametric method of the removal of the annual cycle for monthly data.